is known, the CMB stands as a reminder that the universe still holds many mysteries waiting to be uncovered. The cosmic microwave background, CMB, serves as both a time capsule and a beacon for cosmologists, allowing them to peer back in time to the birth of the universe while also guiding them toward the unexplored frontiers of physics. As much as the CMB has illuminated our understanding of the cosmos, it has also raised profound questions that continue to challenge our most fundamental theories. One of the biggest puzzles tied to the CMB is its connection to dark matter. Dark matter is an enigmatic substance that neither emits nor absorbs light, making it invisible and detectable only through its gravitational effects. Despite being elusive, dark matter is thought to make up about 27% of the universe's total mass energy content, vastly outstripping ordinary matter, which comprises just 5%. The CMB provides critical insights into the nature and distribution of dark matter, even though it remains hidden from direct observation. The temperature fluctuations observed in the CMB tell us that dark matter must have played a significant role in the formation of the universe's large-scale structure. In the early universe, regions with slightly higher than average densities of dark matter acted as gravitational wells, pulling in surrounding matter and eventually leading to the formation of galaxies, stars, and clusters of galaxies. Without dark matter, the ordinary matter alone would not have been able to coalesce quickly enough to form these structures in the 13.8 billion years since the Big Bang. Interestingly, the CMB's precise measurements have allowed cosmologists to infer the amount and distribution of dark matter in the early universe. This, in turn, has helped to constrain various models of dark matter, ruling out certain candidates while favoring others. For instance, one of the leading candidates for dark matter is a class of particles known as WIMPs, weakly interacting massive particles. If WIMPs exist, their presence would have left a distinct signature in the CMB, as their gravitational effects would influence the pattern of temperature fluctuations. So far, CMB data seems to support the existence of cold dark matter, meaning that dark matter is made up of slow-moving particles that interact only weakly with other matter and radiation. However, the exact nature of dark matter remains one of the biggest open questions in cosmology, and future CMB experiments could provide the key to solving this mystery. While the CMB has revealed much about dark matter, it has also led to some surprising insights about dark energy, another mysterious force that permeates the universe. Dark energy, which accounts for approximately 68% of the universe's energy density, is believed to be responsible for the accelerated expansion of the universe. The discovery of this accelerated expansion in the late 1990s was one of the most shocking findings in modern cosmology, and it has forced scientists to rethink their understanding of the universe's fate. The CMB plays a crucial role in studying dark energy because the patterns of temperature and polarization fluctuations in the CMB depend on how the universe has expanded over time. By comparing the observed CMB patterns to predictions from various cosmological models, scientists can infer how much dark energy there is and how it has influenced the universe's expansion. Current CMB data, combined with other observations, suggests that dark energy has remained relatively constant over time, consistent with the simplest model of dark energy known as the cosmological constant. However, there are other possible models of dark energy, some of which predict that its properties could change over time, leading to different scenarios for the universe's future. One of the most tantalizing possibilities is that dark energy could eventually decay or transition into another form of energy, dramatically altering the fate of the universe. If dark energy were to decay, the expansion of the universe could slow down or even reverse, leading to a future where the universe collapses in a big crunch. Alternatively, if dark energy were to increase in strength, it could lead to the aforementioned Big Rip, where the expansion becomes so rapid that it tears apart galaxies, stars, and even atoms. While current CMB data favors the cosmological constant model, future observations could help to distinguish between these scenarios and provide a clearer picture of the universe's ultimate fate. Beyond dark matter and dark energy, the CMB has also sparked debates about the possibility of a multiverse, a collection of multiple, possibly infinite, universes that exist alongside our own. One of the key predictions of inflationary theory is that inflation did not just happen once but may have occurred in different regions of space at different times, creating multiple bubble universes with varying physical laws. According to this idea, our universe is just one bubble in a much larger multiverse, and the CMB could hold clues to the existence of these other universes. In theory, if our universe interacted with another universe early in its history, this interaction could leave an imprint on the CMB in the form of unusual temperature fluctuations or patterns that cannot be explained by standard cosmological models. Some researchers have speculated that certain anomalies in the CMB, such as the cold spot and the axis of evil, could be evidence of such an interaction. However, these claims remain highly speculative, and more data is needed to determine whether these anomalies are truly the result of a multiverse or simply statistical flukes. Despite the tantalizing possibility of a multiverse, there is currently no direct evidence for the existence of other universes, and the idea remains one of the most controversial topics in cosmology. However, the continued study of the CMB, along with advancements in observational technology, could one day provide the data needed to either confirm or rule out this mind-bending hypothesis. The CMB's contribution to our understanding of cosmology does not end with dark matter, dark energy, or the multiverse. One of the most exciting frontiers in CMB research is the search for primordial gravitational waves. These ripples in spacetime were predicted by Einstein's theory of general relativity and are thought to have been produced during inflation. If they exist, primordial gravitational waves would leave a distinctive imprint on the polarization of the CMB, creating a unique pattern known as B-mode polarization. Detecting B-mode polarization would provide direct evidence for inflation and could even reveal the energy scale at which inflation occurred. This would be a groundbreaking discovery, as it would allow scientists to probe physics at energies far higher than anything achievable in particle accelerators, shedding light on the unification of the fundamental forces and the nature of quantum gravity. Several experiments, including the BICEP-2 experiment in Antarctica, have attempted to detect B-mode polarization in the CMB. In 2014, BICEP-2 made headlines when it announced the possible detection of B-modes, which was initially hailed as evidence for primordial gravitational waves and inflation. However, further analysis revealed that the signal was likely caused by dust in our own galaxy rather than by primordial gravitational waves. Despite this setback, the search for B-mode polarization continues, and future experiments, such as CMBS-4, are expected to provide more sensitive measurements that could finally confirm the existence of these elusive gravitational waves. The potential discovery of primordial gravitational waves would be a major milestone in our quest to understand the universe's origins and the fundamental laws of nature. It would provide a direct link between the CMB, inflation, and quantum gravity, opening up new avenues of research into the deepest mysteries of the cosmos. The cosmic microwave background remains one of the most important and mysterious phenomena in cosmology. It has provided us with a window into the early universe, allowing us to test our theories of cosmic evolution and to explore some of the most profound questions about the universe's origin, structure, and fate. From the flatness of the universe to the nature of dark matter and dark energy, from the possibility of a multiverse to the search for primordial gravitational waves, the CMB continues to challenge and inspire scientists as they seek to unravel the mysteries of the cosmos. As we look to the future, new experiments and observations will undoubtedly deepen our understanding of the CMB and its implications for the universe. Whether we discover evidence for new physics, confirm the existence of a multiverse, or detect the telltale signs of inflation, the study of the CMB will remain at the forefront of cosmology, guiding us toward new discoveries and helping us to better understand our place in the vast and mysterious universe. The study of the cosmic microwave background, CMB, has brought us astonishingly far in understanding the history and structure of the universe, but it has also left us with a host of perplexing questions. Among these are deeper inquiries into the true nature of the early universe, the formation of cosmic structures, and the forces driving the universe's expansion. By continuously refining our observations of the CMB, scientists are hoping to push the boundaries of what we know and delve further into the fundamental aspects of cosmology. A particularly intriguing aspect of the CMB is its role in addressing one of the most important unresolved questions in cosmology: the issue of cosmic inflation. Inflation, the brief period of exponential expansion that occurred just after the Big Bang, is the leading
So
theory
yun
to
lang ga
explain
papadas
why the
ko
universe
taga
appears
hagi
so uniform and isotropic on large scales. Without inflation, it would be difficult to explain why distant regions of the universe, which should have had no opportunity to exchange information or energy, exhibit nearly identical temperatures and properties. The concept of inflation, proposed by physicist Alan Guth in 1980, suggests that the universe underwent a period of extremely rapid expansion during the first fraction of a second after the Big Bang. This inflationary phase would have stretched out any initial irregularities, smoothing the universe and leaving behind only tiny fluctuations in the density of matter. These fluctuations would later grow into the galaxies, clusters, and other large-scale structures that we observe today. One of the major triumphs of inflationary theory is that it predicts the exact form of the fluctuations observed in the CMB. The temperature variations seen in the CMB are thought to be the result of quantum fluctuations that were amplified during inflation, creating regions of slightly higher or lower density. These regions eventually evolved into the cosmic structures that fill the universe today. The fact that inflation correctly predicts the statistical properties of the CMB is one of the strongest pieces of evidence in favor of the theory. However, while inflation is widely accepted, it is not without its challenges. For one, there are many different models of inflation, each predicting slightly different outcomes for the early universe. Determining which model is correct, or if inflation happened at all, requires more precise measurements of the CMB, particularly its polarization. As mentioned earlier, the detection of B-mode polarization would provide a smoking gun for inflation, offering direct evidence of the gravitational waves produced during this rapid expansion. Another major question that the CMB might help answer is related to the so-called curvature of the universe. One of the remarkable features of the universe, as revealed by CMB data, is that it appears to be flat, meaning that parallel lines never converge or diverge.